hello everyone. I'm Joe. I know Jaron from when he lived in Madison, Wisconsin. Here, that's where I'm at currently. Yeah, so I guess just a quick background about myself. Well, first, thanks for inviting me. I'll try my best to talk about magnetism. Apparently, Jaron thought I was, at least somewhat qualified to do this, and it's been a little while since I was kind of delving into the magnetism topic, but I hope I can remember enough to kind of talk about it for a bit here. Yeah, I was a student at UW Madison 4 years ago. I graduated with a degree in computer science and Spanish. I was in the computer or the electrical engineering computer science fraternity here. That's where I met Jaron. Um, I was also in this club called Garage Physics, and I was kind of working on some physics projects that were particularly, related to magnetism. So it's always been an interest of mine. Even in high school, I actually kind of worked on some stuff or just began kind of tinkering and exploring with that. It's been 4 years probably since I really worked on much of this stuff, but I was a programmer for 4 years, and now I actually just started going back to community college again. So I'm kind of in the same boat as you guys. So we're all students together. It's pretty exciting. I'm really happy to be back in school, having a fun time. I'm taking Calc 3 right now and a couple electronics courses because I'm studying electrical engineering. Um, that's kind of where I had left off back on my project that I was working on in college. That was the bottleneck to continue, was just my lack of experience and knowledge to quickly overcome these electrical engineering kind of hurdles that I was coming across. So I'm finally made it back, and I'm picking up where I left off. But yeah, so thank you for having me. I guess we'll get into it. Magnetism, and again, I'm kind of fresh in this, recently fresh getting back into this topic. So I tried to put together I didn't put together a PowerPoint. I just kind of opened a bunch of links on my browser, and I'm going to kind of go through them one by one. I wish I was a little bit more savvy on the PowerPoint presentations and all that, and maybe could have came up with something better. But part of my challenge was it's such a massive topic. There's such a big, you could go in so many directions with the talk on magnetism. So I kind of just wanted to kind of go over a couple high level points, maybe try to make some connections that you might not see normally or people might not mention. Kind of some cross cutting things, like physics, they look at magnetism one way, electrical engineers look at magnetism another way, chemists look at magnetism another way. A lot of times they all have different terms, even though they're all saying the same exact thing. So I think that's kind of an important takeaway that I want to underline a little bit here is just like, um, even though there's so many different terms out there and kind of people present concepts in different ways, at the end of the day, it's really all the same phenomena kind of happening. Um, the way that these different disciplines look at magnetism. So I hope that we can kind of look at it through that lens a little bit and make these things seem a little more simple, and then use that to kind of go forward in life and understand things, have more power to understand things, because we understand the basic concepts better. So yes, I'm going to share my screen here. I don't know if I'm already sharing my screen or not.
Nope, nope.
Okay.
Oh, here we go.
Yeah. All right. Here we go. All right. So magnetism. Here's the Wikipedia page on magnetism. This is kind of the classic introduction here. They say there's kind of three types of magnetism. That would be ferromagnetism. That's like your classic iron bar magnet kind of magnetism. And then you have paramagnetism, um, which is kind of the same thing, just not in iron. And then you have diamagnetism, which is basically kind of the opposite effect, where rather than a magnetic field being induced or present, kind of an opposite, an anti-magnetic field, or like a magnetic field in opposition to the one present is induced. So like if I take a bar magnet and put it up against a piece of copper, the copper is actually a little bit diamagnetic. So the copper is going to kind of give rise to a magnetic field that kind of opposes the magnetic field from the iron. So it kind of pushes back, so to speak. Whereas if I take one piece of magnetized iron and maybe a paramagnetic material, so it's a material that is kind of like iron in the sense that it could be magnetized, but it's not necessarily magnetized unless it's in the presence of a magnetic field. I could take a piece of iron and put it near some paramagnetic material, and now the paramagnetic material is going to be magnetized, kind of, it's going to mimic the field from the iron bar, the iron magnet. So yeah, let's continue to this picture here. I think this will be helpful. So this magnetic poles picture here, I
Just let
think it's
me
pretty
bump in a little
useful.
bit.
So
Can you move
basically,
your? Can you hear me? Can
oh,
you
this
move
guy
your?
here, yeah.
Can you move your the pictures like over to the left? Oh wait, that's me. I'm so sorry.
How's it? Can everyone see now?
No, it's my fault. You're completely fine.
Okay, cool. Yeah, also at any point, please feel free to ask questions, or if you can't see something or hear something, just let me know. And or if you want me to try to explain something differently, I'll try my best. Or if something wasn't clear, you know, this is more of a conversation kind of style presentation. I'd like to think so. Yeah, feel free to hop in at any point with questions, comments, concerns. Yeah, so anyway, so magnetic poles here. So basically this is like a standard bar magnet here, like a piece of iron. It's going to have a north and south pole. So what happens if you break it in half? You'll kind of see something like this. You keep breaking it down into smaller pieces. Basically a piece of iron magnet is like self-similar. Like every atom in every iron atom is magnetic in and of itself, and the whole collection is one big magnet together. So that this kind of demonstrates that. um, I think that's kind of important. um, so basically every single molecule, every single atom is a magnet. um, so that's kind of the concept of self-similarity. Fractals, kind of a tangent to what we're talking about, but the self-similarity is the important part. The whole has the same shape as one or more of the parts. So kind of that concept there. Every part of a ferrite or like an iron magnet is a magnet in and of itself. So maybe we just want to go forward with that in mind to some degree. Um, let's see here, back to the magnetism page on Wiki. I can't remember what point. Oh yeah, here we go. So these charts here kind of display that same concept again, just in more of a grid than a single line. So we've bumped up to 2 dimensions here. So a ferromagnetic ordering here. Every single molecule or every single atom, when it's magnetically charged, every single atom is going to be oriented in the same direction. Um, if you have a piece of iron that's not magnetized at all, it will look something more like this. Basically, all the different atoms are going to be kind of canceling each other out, if that makes sense. So this is when we polarize a piece of iron and turn it into a magnet. We're doing this to the molecules. We're making them all point in the same direction. You might hear the term Gauss or degauss. If you go to the hardware store, there's like little things called like degaussers, I think, where if you don't want your screwdriver to be magnetic, or if you do want your screwdriver to be magnetic, you can kind of basically just stick it in like a little magnet tube, and then it will kind of magnetize it or demagnetize it depending on if it's, whichever one is suiting your needs at the time. So yeah, that's kind of what's going on. But really it's in 3D, obviously it's a 3D grid, but I think that illustrates that kind of example well. So there's this concept of domains, like all these magnetic domains are aligned. So here's a great resource. It's called Hyperphysics. Some university hosts this, and it has a lot of great explanations and pictures, and it has equations for everything. So I've used this resource plenty of times in my studies, and I found it really helpful. Um, so that's a great thing to bookmark or something if you're trying to look into this further. Um, but yeah, so the concept of magnetism comes with electricity. You kind of can't separate them, even though we like to talk about them separately sometimes. They're really kind of one and the same. Um, Basically, a moving charged particle creates a magnetic field. Um, so there's our bar magnet again. There's what the magnetic field lines kind of look like. That's a visual representation of those magnetic field lines, which also happens to be kind of, let's say you have an electron or some charged particle. That would be kind of the path that it would take in the presence of such a magnetic field. That magnetic field would exert a force on that charged particle and kind of force it along one of those paths there, you might say. So we can also make, because of this magnetic phenomena, we can also make a magnet out of a coil of copper wire. If we just run an electric current through copper wire in a coil like this, we'll generate the same field. So that's pretty important. Electromagnets. Let me see here. What was the next point? So the magnetic moment. Okay, so this kind of goes back to the concept here of this picture. Each molecule or each atom in like an iron bar, for example, has its own magnetic moment. So basically, it's magnetic in itself, every atom. And what is the nature of this thing that makes it magnetic? Like, why is the atom magnetic, an iron atom? Well, because we like to say it has a magnetic moment. So you could almost think of a magnetic moment as a top, a spinning top. And basically, anything that's spinning around an axis, anything that's spinning is spinning around an axis, right? So because there's an axis and it's spinning around that axis, you can think of that axis as the pole, and it's a dipole. A dipole means there's 2 points on the pole. There's the top and the bottom. So anytime you have something spinning, it's spinning around an axis. That axis basically is the dipole. And polar means like directional. When you hear the term polar, polarized, it means direction has been introduced to this thing. So let's say we have an atom or a molecule of gas in the air that it's polarized. That means basically there's a net direction or of this atom of gas, and that basically means it's going to act as a magnet, so to speak. Basically because there's spin around an axis, so there's 2 poles, and that spin is like directionally, it's directional. Like if you look at it from the top, it's spinning clockwise. If you look at it from the bottom, it's spinning counterclockwise. So the orientation matters. It has a specific orientation. So that's kind of what polarization means. It means there's a specific orientation to it. It's directional. It has energy, which is rotation, and that is in a fixed direction, you might say. So that's kind of what how I like to think of as a magnetic moment. This is like the carrying phenomena of magnetism here is the magnetic moment. And basically it's just spin, it's just rotation. Like think of a top spinning. So that's kind of important concept. We're getting into the kind of the bottom or into the weeds, you might say, of the source of magnetism, but that's kind of right where you want to go if you want to start thinking about what gives rise to magnetism, or what is like the the smallest unit of magnetism. It's kind of just rotation, you might say. So here it is again, a magnetic dipole moment. Kind of looks like you could almost imagine that as just a top there, and it's just spinning. And you'll notice there's a lot of similarities here. If you ever have taken any physics courses or things like that, or even just familiar with some of the language, like inertia, momentum, like angular momentum, some of the equations in language used to describe that is pretty much the same as to describe magnetic moments, because they're kind of the same idea. So I like to think of that as a little top there spinning. And let's see. Okay, where are we? Okay, so precession. So basically, there's kind of, I think it was Euler or maybe Newton, kind of realized there's a few kinds of spin, basically. So you have normal spin, and then imagine if this axis was perfectly vertical, that would just be standard spin. But now you tilt the axis a little bit and you start to spin, and this whole axis is going to kind of rotate. That's called precession. And then you can take it 1 degree further. I mean, you can probably take it to infinite degrees, but it's like one more level of rotation. Basically each term, like there's spin, and then you go one more level of spin, that's precession. You can take that again, and it's nutation, it's called. So here's the illustration of that. Like if this thing was perfectly vertical, it'd just be spinning. But because the axis is also now spinning, the axis itself is drawing a circle. Kind of, you can imagine this top of the axis here drawing a circle if there's like a piece of paper up there. So that's precession. So that's kind of important. Let me see if I can pull that up. I was looking for like a better resource that just kind of explain this like really simply at a high level. Yeah, I would, if you're interested in that concept, I would look further into that. Spin, precession, and nutation. It's all basically just spin, but it's kind of the different ways spin manifests, or rotation, you might say. So that's kind of important because the way things rotate and spin kind of is the root of their like physical behavior, especially in chemistry, and like molecules and atoms and such. So here's nutation. That's like the third order spin. So it kind of is the same idea. So you got green is rotation here. This illustrates it kind of well. The green is the rotation there, just around an axis, like your classic spin. And then blue is precession. That's this arrow here. So the whole axis itself is rotating. And then nutation is this little sine wave kind of going around this precession circle. It's just one more cycle of spin happening, basically. As this, it's basically spinning on one axis, and then that is spinning, and then that itself is spinning as it goes. And you could actually keep nesting in, like if you zoomed in and this thing was spinning to a 4th degree, like there's a 4th order of spin, you'd zoom in on that red line and it would look like the red line itself was like a sine wave. Like it is a sine wave, but if you zoomed in, you'd see that the line was a sine wave. There would be a sine wave inside of the sine wave, if that makes sense. So you can kind of keep taking more and more degrees of spin as you like nest in or zoom in. It's kind of spin all the way down, you might say.
Hey, so how does this the spin? How does it relate to magnetism?
Okay, so we're getting to that. That's a good question. That's important. That's an important question to ask. So how does it relate to magnetism? Basically, let me skip forward a little bit. So there's this thing called basically spin waves. So we're kind of getting in really deep here to like what is electricity, what is magnetism, how does how does a electromagnetic wave propagate like through a wire? Like how does electricity go through a wire? Like you might see classic examples where they'll say, oh, it's kind of like water. Like water comes in one end, and then imagine you have a hose full of water. You put some more water in one end, some water is going to come out the other end. And they kind of say that is like electrons, like, and they say electrons are moving like all throughout the circuits and whatnot. But really, that's not exactly how it happens. It's a great model. It's a great introduction. Um, but if you try to take that model further and use it to understand even more complex things, it's not really going to hold up well, and it's not going to serve you. It's not going to serve your understanding. So I'm just, if I'm going in too deep, then we don't definitely need to go in this deep. But basically, if you want to take it a little deeper than some of the introductory models, basically the way these it's basically a bunch of dipoles. So like I mentioned, a dipole, right? It's just you take something, a particle, a little chunk of space, you might say, that's rotating around an axis, and that's a dipole. And the way these dipoles are spinning in their orientation, that basically gives rise to the phenomena of magnetic domains and electromagnetism. Like the spin and the axis is the magnetic moment. So you get into some kind of more advanced physics, and they start talking about things like spin waves, or they'll say things like magnons. And there's all these crazy things in terms and concepts of how magnetism and electricity kind of flow through materials. But really, it's the same fundamental principles here that we're working with, no matter what kind of they call it. Here's an illustration of a precession spin wave. So it's kind of the same deal. It's really just the axis of the magnetic moment is kind of just rotating around the circle here. So that's precession, right? That's this happening right here. So when we see, imagine if this was an iron atom and it was perfectly vertical, that's kind of just like your classic bar magnet. But now let's say you like disturb it. Let's say you take another really strong magnet and pass it by the bar magnet. It's going to create a disturbance, and that disturbance is going to basically manifest like this here. It's going to wobble the axes of rotation of all these dipole moments of iron. So you take a standard magnet, and it's going to be sitting, a standard bar magnet, all the little arrows are just going to be just like that, nice and straight. But then you maybe put it in the presence of a really strong magnetic field for a moment, for a brief second, you disturb it. That's going to basically cause this kind of disturbance. Every atom is going to start to wobble. Every arrow here is going to kind of start to wobble, just like this top. So that's kind of like a precessional wave. So that's like what a magnon is, basically. And the same goes for these, the spin wave here. So these are different modes of transmission of electromagnetic force through different materials. But really it's these kind of like Newton and Euler, these mathematicians and kind of classic scientists, they had incredible insight because they kind of understood the fundamental principles of all of nature. Kind of, you can really boil it down to some very simple kind of concepts. And then we kind of course, we study it, and then we have all these crazy terms and explanations that kind of just tend to make things more complicated sometimes, unless you're in a very niche. Then it can help facilitate communication between scientists who are working on like very particular problems. But for us common people, we want to go understand cool things, and we're kind of prohibited from understanding it because there's all this specific terminology. But really, it's kind of simple concepts. If we can peel away kind of the tricky language, there's really simple concepts hiding underneath there. So basically the point is, a lot of this stuff, even if it seems complicated, it really makes sense, and we can make it make sense if we do our research and break things down in small pieces.
Yeah, thanks, Joe.
Yeah.
Thanks.
Just letting you know, we have 2 minutes. So
2 minutes? Okay, sorry. I'll try to hurry up. Let's see here.
don't worry.
So Self-similarity, we already kind of talked about that. That was kind of important too, because so here's the force for electric. Basically, you take an electron or something, a charged particle. Here's the equation that describes that. This is a constant. So we can kind of just ignore that. That's just like a one number. It's always the same number. This is basically the force between two charges is going to be equivalent to the charge of one and the charge of the other over the distance. The radius is the distance squared. So why is that interesting? Well, let's look at the equation for gravity. It's this, it looks exactly the same. So this is a constant. It's always the same number. We can kind of just ignore that. So what is the force of gravity between two bodies? It's the mass of one and the mass of the other over the distance squared between them. So kind of the same exact thing, right? So that's basically like the equations that kind of govern nature are kind of scale free, you might say. It's whether you're looking at planets or whether you're looking at electrons, it's kind of the same behaviors and same patterns of motion. So here's something cool, which is vortexes. So this is actually, we'll just watch this for a second. So basically those rings you see there, that's actually a good model for electrons. And basically like photons, like they say, like wave particle duality, for example. It seems crazy, like very mystical, like, oh, things are behaving in ways that can't be explained, but really it can be explained, and it's really not as crazy as it seems. Like, for example, a smoke ring. Let's find a shot of the smoke ring here. Yeah, that smoke ring is an example of a wave and a particle, right? It's like one particle. It's one unit, one piece. You can point to it. It's got like a fixed position, you might say, but it's also a wave. It's rolling through space. So yeah, it looks like it's 9:30. I didn't quite get to everything, but there's quite a lot to get into here. So I don't know if there's other questions people have, but
Yeah, that was excellent, Joe. Thank you. It definitely. Oh, here's Jade.
Jade.
It spiked my interest in magnetism, and it I'm not sure where magnetism comes myself, so comes from. So uh, it's just an interesting thing to look into. Yeah.
Hey, Joe, I wanted to say thank you. I appreciated that.
for sure, yeah, I was totally happy to do this. Yeah, here's just a couple quick pictures, I guess. So like, I thought this was pretty interesting. So basically, I took basically I got like a little, just a quartz crystal pyramid, something like this. There's just a little pyramid, right? And if you get them out of like quartz crystal, basically it creates a field just passively, because quartz is polar, kind of like that ferrite. It's got a magnetic moment to it in a sense. And this little dish of water I just put above the tip of the pyramid in my freezer, and then I froze it. And you can kind of see these field lines frozen into the water there. You can kind of see their pattern in the water. So that's a kind of an interesting experiment. I had seen people talking about this and I didn't believe it. I couldn't believe that something like that could happen. And I did it for myself, and lo and behold. So, and here's the project I was working on back in college. It was basically a coil, a certain kind of coil, to basically create a special magnetic field pattern that kind of had some interesting properties, to put it simply. So this is kind of what I was working on, and I put it in the closet for 4 years, and I finally just pulled all this stuff back out now that I'm studying electrical engineering. So I get to start working on this again, and I'm pretty happy about that. So
Cool.
we're all
Yeah.
studying.
So hopefully we spiked your interest a little bit.
Yeah. Oh yeah. You definitely did. I just having this opportunity to talk about magnetism got me pulling out my old notes and trying to review everything and think of things to say that were interesting or beneficial or help to understand, help understanding. So yeah.
Yeah. Yeah. So thanks for coming.